Hi, folks. This is Lab 7 in the week 7 of the semester, and uh, it's going to be simulating the following two problems. There are two things that I'm going to do. One of them is called the uh, slider crank mechanism, and the other problem is going to be the sliding ladder problem. So we go through these one by one. Well, here is the sliding crank mechanism, and you can see that basically we have a mechanism involving a connecting rod, a crank, here's a crank, a connecting rod, a piston, and a piston path, which you can assume that it's the ground and it's not moving. So once again, base, this base is going to be the piston path, block, which is going to be the piston. Here is the crank, and there is the conrod or connecting rod. So as the crank turns, it makes this piston go up and down the path, and we are trying to get uh, the, the mechanism associated with that and get some graph, for example, given the speed of the crank, what is the acceleration of the block, etc. The second problem that I'm going to be doing is a sliding ladder. So we have this ladder leaning against the wall here and also sitting on this floor. And the ladder slides down and making the foot of it goes to the left. Okay. This is going to be the second problem. Now, this is the kind of thing that your calculus prof, for example, did under the sliding ladder sliding ladder problem or related rate problem. And he showed that based on the fact that the length of the ladder is constant, you can assume that z squared plus y squared is equal to L squared, which is the constant, the length of the ladder. And then if you differentiate this thing, you get something like that. And if you know one of the velocities, if you know the downward velocity, for example, you can plug it in and you get the or horizontal velocity. If you know the horizontal velocity, you can put it there and get the downward velocity. So velocity is not constant. Only one of them you can assume is constant, either horizontal or vertical, and the other velocity is definitely not going to be constant. All right, so these are the two problems we're going to be doing. Let's do the base first. So insert a new part in there, and I'm going to call this thing the track. I think I called it the track, right? Or base. I called it the base actually. Properties. I'll call it the base. Base and base. All right. Let's make it. So on that vertical plane, I will sketch just so that the angle looks the way the view looks like the one that I showed you. Yeah, okay, I suppose we can do it like that. That's fine. So dimensions are 1 and 1. Exit padded by 10 inches. Okay, and I have a pin here on the side. Okay, on this side I will sketch. I'll put a little circle here. The diameter of this is 0.5, which is radius 0.25. Okay. I'm not going to bother making it centered or just leave it the way it is. Exit. Now pad it. It looks like I want a padding in that drawing. The padding is 0.5, I believe. 0.5. Okay, good. Let's go all the way to the top. Click on the floppy so that you save it in that same folder. Let's do the crankshaft. So insert a new part in there. Always say no. Change this thing to be crank, and crank. Say OK. Double click on this. And on that plane, I will sketch, well, a circle this size, but the easiest way to do that is actually project that circle. There we are. And now we're going to make the rest of the crank. So the rest of the crank is very simple, actually. There's several ways of doing this thing. One of them, the easiest way, maybe actually to do it with a elongated hole. I like that. Usually I draw a profile and then I clean it up. There we are. Okay, this is the lazy way of doing it. Now let's clean it up. So for example, I want this circle, control that circle to be concentric. There we are. And in the drawing, it seems that I'm indicating that the diameter of this circle is 0.75, although that really doesn't matter. But in case you want to put a diameter here, right there, cancel. This diameter, half of 0.75. So 0.75, that's actually radius, divided by 2. Oh, what did I do? 0.75 divided by 2. Okay, good. Now, center to center, it seems that is 3.5, so I will make a dimension from here to there. 3.5. All right. And then finally, I'm gonna draw a circle here. You do it any way you want. This is how. Oh, wait a minute now. What is this? This is actually the connecting rod. It's not the crank. This is the connecting rod. I will fix that. Okay, so this thing is. I'll fix that. Okay, so this radius is 0.25. Okay, and let me pad this thing by 0.25. Exit and pad it by 0.25. Yeah, 0.25. And say OK. Now the only thing is that I didn't want this thing to be the crank. I want it to be the connecting rod. So I'm going to change it right here. Properties, conrod. Okay. And conrod. Okay. So let me go all the way to the top. Click on the floppy so that it's saved. All right, let me move these things away from each other. So I'm translating it that way. Okay, fine. Now I'm going to make the. Honestly, I don't know. Is this the. That was the crank. Ooh. All right, let's go back here. Right click properties, crank. Okay, and crank. Good. So I was okay to begin with. Now my connecting rod is right here. So this is how I'm going to do that. All right, so maybe what I should do is on that face, let's go all the way to the top, insert a new part in there. Say no, that's going to be the conrod. properties, Conrad, and Conrad. Okay, that's good. Let's make it. Double click. Now, on that face, you do it any way you want. This is how I'm going to do that. On that face, I'm going to sketch a circle that size. So why don't I actually project that? I project that. There we are. You can see that right there. And to do the rest of this, once again, there are different ways of doing it. So let me hide that piece in the back. So let me do this once again, this thingy, the elongated hole. I'm going to clean it up. So this circle, control that circle. We want them to be concentric. Okay. That radius, we want it to be 0.75 divided by 2. Yep, divided by 2. I did the same mistake here. Let's try it again. 0.75 divided by 2. Ah, good. That's better. Now this length is, connecting rod length is 6.5, okay? So dimension, I dimension this. Can I dimension that? Yep, 6.5. 6.5. Okay. And I need a radius here, another circle at this end. Radius of 0.25 or diameter of 0.5, either way. That's the radius, so 0.25 will do. Okay. Now, exit. Exit. Now remember, my crank is actually in hiding. You can see it's back there, but I don't need it. That's okay. But what I'm going to show you here is that I want on this side to be a little pin sticking out. So of course, if I pat it now, there will be a hole here, okay? But I want it to be something sticking out. So here's what I'm going to do. You can do a multi-pat, for example. You select this. It says that there are 3 circles here. There is this one, which is the big one, the big boundary. So I want that thing to be 0.25. There is this one, which is the thing on that side. I want that thing to be a hole, so I just leave it as 0. And this one, I want it to stick out by some length. For example, I don't know, maybe a point, I can't remember. What is it that I have there? It says 0.35. Okay, fine. I'll make it, close that. Here, 0.35, okay? Say okay. Now you can see. The only thing is that the direction of it was incorrect. So let me go back here. Let me go to that multipad. If it's too much of a hassle for you, you do it any other way that you feel comfortable with. There we are. Ooh, still doesn't look very good for me. So what I'm going to do is I'm going to go to that multipad. You know what? I'm going to do this. Oh, okay. So this is fine. Maybe I do it like that. Second limit. Okay, so I'll put down a 0.25. Oh, this is getting too much. So you know what? I'll put down 0.35. Let me go back here. I'll tell you what. I'm going to leave this thing as 0.35 plus 0.25. That's 0.65. How about that? Look, there are many different ways of skinning a cat. You do it the way you want. Okay, if this is too much of a hassle, do it the way you want. Good. Go there, Click on the floppy. I regretted doing it this way. So let me see now what happened here. Click on the floppy. Impossible to save. Okay, already existing disk. Let's go here. Where are we now? Conrad, crank. Okay, that was a Conrad. Yep. So what is the issue here? Let me see for a second. I wonder what's going on here. File, save management, base is open. Conrad. Oh, there's two of them modified. Okay, so yeah. So let me do this. Save as Conrad. Correct. Because I kind of got distracted by that business and all right, let's find out what's going on here. All right, so let me go back to that folder. That folder was July, supposed to be July 4. This is the correct one. This one I don't want. I'm going to delete it actually. Okay, so go back here. No confusion. There shouldn't be any confusion. If you go to File, Save Management, yep. So this is the product. Save as. Let's make sure that we have saved everything. All right, good, good. Excellent. And there are things that like this that can happen to you on the test. Make sure that you master this process so that you feel comfortable. Okay, do it any way you want. All this happened because I got distracted by that multipath. All right. Okay, good. So let me go ahead up here, and we want now the what is it? The block, right? The piston. Let me hide. Let me bring it in the front so that we can see things. Now notice that it's not coming back. So if that happens to you, go to the tree and do it from the tree. Okay. All right. There we are. Let's separate these things. So I'm going to translate this thing in the y direction like that. All right. So here's the situation. This hole is going to go into that pin. This pin is going to go into that hole, and then we're going to do the block. Okay. So we're going to go up there, insert a new part. No, we're going to go here, call it the block. Or the piston if you want. Good, let's make it. It's very simple. So basically it is on that plane, I will sketch. Okay, and once again I didn't learn my lesson, so I'm going to make another multipath. How about that? Bad idea. But anyway, so let's put some dimensions here. Okay, and inside of that, I will draw a circle. If you want, you can center it, but it really doesn't matter here. This dimension, 0.25, and you know how to center it if needed, right? You should. Okay, exit. Now I'm going to do a multipath. So there's this guy, which is going to be 1 inches. And there's this guy, which is going to be, I don't know, one, maybe 2. Oh. Let's go back. Back. This one was 1, right? So it was supposed to be 1. Fine. This guy was supposed to be 2. All right. Maybe it's a little bit longer than what I wanted here in the drawing, but because this says a length of 0.75. Okay, if that is the case, let me go back here and oops, no, in the multipad, 0.75 plus 1, so that makes it 1.75. It's a little bit short. Good. So let's go all the way to the top. Use the floppy. Save everything. Okay, so now we're going to do the assembly process. Okay, where are these things? First thing I'm going to do is to anchor the space. So click on the anchor, the space. Good. Then I'm going to put this crank on that pin. So coincidence between this axis and that axis, and coincidence, for example, between this plane and, if it makes you feel more comfortable, take that side. But with these arrows, you can actually control which side you want to take. So if you update, there we are. The only thing is that I would have preferred if, okay, so let me show you what I mean by controlling it. If you go to this last one and you flip on the arrow, flip the arrow, say okay and update, that's how it's going to look like. I did not have to be very fussy about which side I pick. You can control it with those arrows. Now, coincidence between that axis and this axis, and coincidence between this plane and that plane. Once again, if things don't look right, flip the arrows or go from same to opposite. Either way. Let's check this out first. It doesn't look good. Double click, flip the arrow, say OK, and update. That looks better. Okay. This is too long, I think, because notice that I didn't want it to be that long, so let me go ahead and change one of these dimensions. We can go actually to this was what? This was the Conrad, right? So we go to the Conrad, and I believe it was this sketch, right? Yeah. Okay, so let me change this thing to maybe 5. Exit. Yeah, that's ooh, this is because I did not yeah, because of the way I did it. So let me go ahead back here and fix it. So let's go back to that sketch. Yeah. So I make this control that concentric. That's why it just stayed there. Yeah. That's a lot better. Very good. Now we're going to put this this block over there. So for the block, we say let's go back all the way to the product. Coincidence between that face and yeah, that face. Okay, update. All right. And now coincidence. Here, let's do this. Coincidence between this edge and that edge. Update. Good. Now, if you wanted to end up on that, you just move it manually. So this is translation direction X. If it makes you feel better, go like that. And this, yeah, pretty good. Okay, now, as far as putting this hole on that pin, all you need is a revolute joint. You really don't need the, you need a cylindrical joint. You don't need the revolute. All you have to do is to say axis to axis, okay? So coincidence between this axis and that axis, and update there. Okay. First of all, let's save everything. How can we make sure that this is actually reasonable? So let's go to that move toolbar, manipulate, check this box, which means respect the constraints, and then let's do a rotation. This is a free rotation about that axis. Now things must move the way it is. If not, obviously the mechanism that you're going to do is not going to work for sure. But this is fine. This is fine. Okay. Let me say okay. So now we're done here. We're going to go to digital mockup, DMU kinematics. Get the magic wand out. Where's the magic wand? Right there. Remember, these are the important, very important toolbar. Knowledge is later on for putting physics into it. So I'll put it just, yeah, okay. Just leave it there. No problem. Okay, magic wand out. New mechanism. You can give it any name you want. Why don't I call this thing slider crank? This is just a name, slider crank. How about that? Okay, slider crank. Say okay. Auto create. Notice that the joints are created. There are 4 of them. Oops, not there. Let's go here. Mechanism, slider crank, degree of freedom is 1, 4 joints. Prismatic one is this block. Revolute between base and the crank. That's the revolute one. Revolute between conrod and the crank. That's this guy. And then the cylindrical one, because all we did was made axis of this cylinder coincident with the axis of this hole. That's why it became cylindrical. Now, the 1 degree of freedom, because if you move the crank, the whole thing will move. So go to this crank and the base, make this thing angle driven, going from 0 to 360. We say okay, your best friend pops up. Let's do a simulation with command. Manually we do this. So let's check it out. Does it work? Yep, that works. That works. Good. I always reset. Now create a simulation. Slider crank. Remember, you drag this thing all the way to the end. Insert, rewind, change this thing to anything that you want. Anything but 1, not anything that you want. And then if you want this thing to go continuously, make sure that you use the correct loop change mode, which is arrow chasing each other, and just play. Good. So we have done a cartoon. You stop this, you rewind it, you say okay, the simulation has been created. Okay, good. Now, by the way, I want to find a trace of a point on this part. On this part is the connecting rod, okay? So I move to the part design by double clicking on that part, and I create a point anywhere I want on that surface. See, it's on a plane. I selected that plane. There we are. So this point must be on the connecting rod. If I want to get a trace, go back to the product meaning DMU. Now that you have actually created the simulation, you can go and compile it. You know how to compile? Same place that you did the simulation. There are other icons. You just click on that. And we want to generate a replay. I don't want to generate animation file, so that's good. And don't use a 1, use anything but 1, and then just play it. So what happens is that the replay has been created here. So you can show it to your friends, you can show it to your supervisor, etc. if you want. Good. Now we go and do a trace right there. You see that? Trace, click on it. It says element to trace out. For example, this point, that's the point that remember, this is the point that I created. And reference product is just the product, 26 points. So we say, okay, there we are. Now, make sure you save this. So file, save management, trace, save as in that same folder, which was called July I was going to call it July 4, but it's July. You say okay. Let me close that. Now I'm going to say insert existing component in there. It says which one? It's obviously the trace. There we are. Now if you play it, you see that that point, this point will actually go through that. If you replay it, right there. Okay, so let's do it continuously. Let me slow it. Oh, this is too fast. I don't want to do it like that. So rewind. Let me do that manually for you. So I go to simulation with command. There is the point that I created. And if you look at it, that point is right there. And it is going to move, that particular point is going to move on this trace. Reset. Now let's put some physics into the problem. So first of all, we save everything. Click on f of x. We don't want everything. We want the stuff only related to the mechanism. So click on the mechanism. Just these two. This is the angle of the crank. Add a formula equal to, if it's 1 cycle per second, or 2 pi radians per second, or 360 degrees per second, that's what I'm going to type. 360 DEG underscore S. So 360 degrees in 1 second times time, variable time is right here, but this is the name of it. The reason that actually came to be slider crank, because I renamed it from mechanism 1 to slider crank. If I had left that name as mechanism 1, this would have said slider. It would have said mechanism 1 10 times. Say okay. Assuming that there are no syntax errors, etc. We go here, and now you go and do simulation with laws right there. I don't want to do it 10 seconds. I'll do it 2 seconds. You click on the 3 dots here, make this thing 2 seconds, and then play. There's physics here, but you may say that I don't believe you. How do I know it's physics? Just like the one that I did before. The only way to do that is actually to plot stuff. For example, first you need to go and create sensor right there. Speed acceleration sensor. See that? Speed acceleration sensor. You click on it. You give it a name. So reference product is that base. The point, for example, well, I can select this point. It's going to be the this point that I want to plot something about. You say okay. Notice that it has been created here, right there. Now you go through simulation with laws, and you say activate sensor. And what do I want? For example, I want the acceleration. Let's do two things. Let's take that point. Velocity of it and acceleration of it. Okay, so what does that mean? The magnitude. When I say the magnitude, means that I'm not going to give you x component or y component or z component. So velocity is this linear speed right there, linear speed. You turn into yes. And acceleration, the magnitude of it is just linear acceleration. Okay. Now there's one more thing that I'm going to ask for. You'll see why. I'm going to ask, for example, let me ask for one thing. See this uh, 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 slider crank? What is that? Slider crank. This one. Slider crank joined Revolut 2. Which one was the one that I had Revolut 2? Actually, it was. Which one did I fix? Yeah, it was Revolut 2. Okay. So I'm also going to ask for revolute 2, which is the angle of that crank, okay? As a function of time, that angle will grow, correct? Okay, goes from this 0 to 360. Now, move this thing down and play it twice. When it's done, you go here, you say graphics. So let's check what things are. What is this yellow one? You click on the yellow one, it says the angle of the crank. It goes from 0, it goes 2 rounds, and it's going to be 720. You can see that. The angle grows and grows and grows. It traverses 720 degrees. If you go to this one, this is the acceleration. Remember, move these, zoom out. This is the acceleration of that point. Acceleration of that point, the red one. Acceleration of that point. And you can see that the magnitude of the acceleration, okay? Because it goes positive, negative, it slows down, it speeds up, but it's that red one. This guy is the speed of that point, okay? It's the green one. And once again, it's both positive and negative, but because I'm doing the magnitude, it just shows these things. Now remember, if I ask you to generate these plots, once you get this thing, you go and do print screen, and you create a, for example, a Word document. You can do it in Paint also, so paste it, home paste. Make sure that we can see the units here. Make sure we can see the numbers here, okay? And then save it. File, save as. In that folder, which was July, wherever I put my stuff, desktop, July, I'll call it my generated plots. Okay, so this thing is going to be in that folder. Now, suppose I want to, oh, I'm done with this. Suppose I want to generate the velocity of this point versus the acceleration of that point. So it's not versus time. Those plots that we just stored were versus time. So what you do is, first of all, you rewind. You clear the history. See that? You clear history tab, clear it. Okay, let's go back here. History tab, see history tab, clear it. So there's nothing there. And now you're going to say options. See that? Options right there. Customize plot, add, and go and pick the things that you want to plot one against the other one, assuming that you already asked for it. And I did ask for linear speed, and I asked for linear acceleration. Where's that? Linear speed. Where's the linear acceleration? Linear speed. And you say, okay, if you had not asked for these, you will not be able to do this. You say, okay. Okay. All right. And then you say, select it, close, and graph it. Ooh, I guess, yeah. Let's play it first. Let's play it. Let's play it. No problem. Play it. And now graph it. There we are. So this is the plot of acceleration versus speed. Magnitude of the acceleration versus magnitude of the speed. Notice that the vertical axis is inch per second squared, magnitude of the acceleration, and this is inch per second, magnitude. Now, again, print screen. If we had asked for this, you've got to give us that plot, and I will ask for it on the test. So, print screen. You go to that folder. You go to that file, or you can create another Word document. Home, paste. There we are. Please make sure that you only give us the plots that we are asking for. If you give us the plot of something that I did not ask for, you will lose some marks, unfortunately, on it. Okay. Now, let's check it out. This is done. And rewind this thing. It's all done. I save everything because I'm going to do my second problem. Okay, let's check our folder here. That folder was right there. There is that generated plot that I asked you to do with Word document. You can double click on it. Then we can look at these and hopefully give you a perfect. Okay, let's do it in that folder. Put everything in that folder. All right, let's insert the wall first. So actually, I'll do the ladder first. So insert a new part in there, and I'm going to call this thing the ladder. Right click properties. The name of the part is down here, or part number. Oops, right there, ladder, and the instance is up there, ladder. Okay, we make it. Double click on the part right there. You're in part design, so on a convenient plane. Let's say on that, on that plane. Why is that plane? I will draw something that looks like my ladder, and it looks like so. We'll dimension it in just a minute. Now notice that I was going to make a circle here, and I missed the opportunity. Left click, hold down, and drag a little bit. But that's okay. You can always go to here to sketch tool and clean it up right there. See that? We come down here, and then left mouse button down, drag it a little bit, and it turns into a circle. Otherwise, you do it with what I just showed you. Okay, let's put some dimensions and dimensions. This line is 7. Wait a minute. What was it? 7. Yeah, 7 inches. 7 inches. And these radii are 0.5. If I change this thing to 0.5, the other one, I think automatically is, well, it didn't because I don't have a parallel to straight, so that's okay, 0.5. There, this is the ladder. Exit. And I'm going to pad this thing by, let's say, 1 inch. Okay, so pad it by 1 inch. Uh, make it 0.5 inch. 0.5. All right. The other thing that I'm going to do, I'm going to create 2 points, one at this end, one at that end. So let's do in this part, in this ladder part. So click on the point, and there are different ways of making the point. So I'm going to use the circle and sphere ellipse center. So I select that. So notice that the point is going to be created right there, and I do another one on the other side. The reason is that I want to find the velocity of this point, for example, while the point on the top is sliding down uh, the wall, kind of. So this is taking care of it. So let's go to the product immediately, product level. See that? Double gear, click on the floppy, and this part is going to be fixed, or not fixed, but saved. So insert a new part, say no, and I'm going to change this thing to wall. Right click properties, wall, and wall down here. All right. So let's double click on the wall. We're going to go into part design. I'm going to be making the wall. So on this vertical plane, I will sketch something that looks like the L that you have, making the wall. So perhaps something like that. There is the wall. There. Exit, and once again pad it. Let's make it 0.5 inch. 0.5 inches. They don't have to be the same width. In fact, the width has nothing to do with the kinematics of the problem. Now, you might wonder why, but just be patient and you see the rationale behind what I'm going to do. Notice that this point, when the ladder is leaning against the wall, the way I've constructed it, this point is always half an inch away from the wall. And that point is always half an inch from the horizontal wall. Now, I'm not going to worry about that because I will do slide curve joint, which is that curve at the end slides along that line. But for this point, I'm going to do a point curve joint. So I'm going to draw a line, straight line here, which is half an inch from the wall. And eventually I make that point to always slide, not slide, but move along that line. So here's the reason that I'm going to make this line for you. I just explained it. So on that plane, on that vertical plane, I will sketch a line like that. Okay, something like this. I'm going to make sure that it actually goes, it touches at the bottom point. So, so this point, although it's not important, but I will do it anyway. This point, control that point, that line. We're going to make it coincident so that it lifts it down and puts on it. Okay. And let's see now, this thing, let's make it about 8 inches. Okay, 8 inches high, maybe 9 inches high. There, I'll make it 9 inches high. All right, fine, 9 inches high. Very good. That's pretty much it. Exit, and that's it. So let's put it in the good isometric view. Excellent. We go all the way on the top, all the way on the top. Click on the floppy. Everything. Oh yeah, I forgot to actually put this thing half an inch away from the wall. So let's go back to that sketch. I forgot. It just it looks nicer when we do it like this. So the dimension from this line to that line, half an inch, 0.5. Good. Now exit and save. This is in case the CATIA crashes, power is lost, we have stuff. Okay, let's go to product, double click on the top line and then floppy. Okay, good. So now we're going to go, assembly constraint. The first thing we're going to do, we're going to fix the ladder. So use the anchor to fix the ladder. This is assembly constraint. What I've done here is close the stuff that I don't use very often for these problems. So I've constrained, which is extremely important. And I don't even need this. I don't even need that. Okay, so we have the move toolbar and update. Okay, and a split in case I need it. I just erased. I just closed everything else that I don't need. All right, good. So we're gonna go to we anchored this. Now we're gonna put this point on that curve. So point coincidence between this point and that line, and update. Okay, good. Now this, I want to bring this surface and put it on that surface. And the way to do it is by using the contact constraint that we have not used so far in the course, in this part of the course. That's not the same contact as FEA. So that face and this face, notice that there is external and internal. This means that they're externally going to be contacting each other. If one doesn't look good or doesn't look right, change it to the other one. But this is, I'm sure it's going to be okay. Right. The only thing is that I don't want this guy to be at the bottom. I'm going to move this thing up. So let's use the move toolbar and manipulate icon, and make sure this check box is this box is checked, because when I move this thing up, translate it up, I want these two to remain in contact with each other. So I'm going to say translating direction Z. This is direction Z. I'm going to drag this, and notice that when I move it up, because this box is checked, these two stay in uh, contact with each other. Otherwise, if I did not do that, this ladder would horizontally move up in a horizontal position. Okay, good, good. Let's make sure one more thing. I noticed that it is possible that for some reason, because of what I did, these two are not flush. Okay, you can see that. I want them to be flush, or these two are not flush. So to do that, I can say coincidence between this face and that face, and update. It will push this thing in. Let me move you. Let me show you here. Right now, it's off that plane. But when I made coincidence between this plane and this plane, and I update, it just pushes it, and everything is going to be the way they are. And this last one, actually, I really don't need it. Okay, I can delete it, because you will see if I left it there, it will lead to what is called a planar join. I'm gonna delete this last one. Okay, good, and that's pretty much it. So let's save everything. So now we're gonna go to uh, digital mockup, DMU kinematics. We're gonna go into the new workbench, which deals with kinematics and stuff like that. So let me move these things out of the way. And I don't need this. I'm going to close the stuff that I don't need it. The important things that I need are these toolbars that are kept here on the top, okay? And of course, in case I need the update is also there. And this knowledge toolbar. This knowledge toolbar generally in the utility position, uh, row at the very bottom. Okay, good, good. Let me also move the knowledge up, because if you want to put physics into the problem, you need this knowledge toolbar. All right. Now, first of all, I put some constraints in my assembly design, and I want to turn them automatically into joints. So you click on the magic one, this auto create, new mechanism number one, auto create, and you see that some kinematic or some mechanism was created. The degree of freedom is one. Let's look at our joint, and you'll be surprised. It says revolute joint. If I had not deleted incidentally that other constraint, you would also get the planar joint probably. And though this is totally nonsense, okay? It happened because of what I have here, and I don't need it, so I'm going to just delete it. Just gone. I don't want to delete the constraints in case I ever have to go back to the assembly constraint and I need it for. Oh, they say I should have said do not delete. Yeah, just a second. No, cancel. I want to delete this. Do not delete the children. Do not delete the children in case I ever need it. Okay, good. That joint is gone. Now, what you want to do is to create a point curve joint. So if you look in this toolbar of all the joints, you have the point curve joint right there. In order to be able to create a point curve joint, the point must be on the curve, and it is. If not, otherwise you get a message saying that there's a gap distance between the point and the curve, and you won't be able to do it. But here it is. It is the point is on the curve. So curve is this line, and the point is that point right there. Okay, say all right. I will come back and do this thing length driven, but not now. We'll do that later. And then, although I could have drawn a line here and that this said this point stays on that line, another point curve joint, I'm going to do it a different way. I'm going to do it using slide curve joint. So this curve slides along that curve. By the way, notice that this doesn't have a command associated with it. Point curve does, but not slide curve. We say okay. So here we have a point curve and a slide curve. Degree of freedom is 1. And in order to do the rest of the problem, we have to turn this thing into 0. Now remember, slide curve does not have a command, but point curve does. So double click on it, make this length driven, okay? And then we say, okay, mechanism can be simulated, and let's see if it works. So here is the simulation with command manually. Single degree of freedom. Incidentally, notice that this did not start all the way from 0, because the 0 of this line is way on the top. Okay, so it's actually at this location that I brought it to is 4.1248. This comes into the play later on. So let me record it here. 4. Well, I have to write it down because we're going to need this number later on. 4.1248 inches. That's because when I put the point on the curve, I just happen to select that location, and that's what happened. Now, good. Okay, so let's see. You go this way, this goes down, and obviously you go this way, it goes up, further up. Okay. Now, if you want, you can put this thing in the very top, and in fact, this is what I'm going to do. Okay. If it's bothering you, and you want this thing to be, somewhere on that wall, you have two choices. You can make this the length of this wall higher, or because this wall, this vertical portion does nothing. It's just this line is doing all the work. Okay. So if I put it at position 0, then I guess I don't need that 4.1248 anyway. So we say okay, starts there. Let's double click on it. Oh, not this. Yeah. All right. Now, so obviously it is manually it is working. Let's go and create a simulation. Mechanism number 1. This is even not at the point, see, this is not at the point 0, it's 1.5. So this distance is 1.5, and I need this number, 1.5. 1 point, I may need this number, 1.53. Okay, good. So we say, okay, let me see if I drag this thing. It doesn't make a difference here. Reset. Okay, good. 1.53. So that distance is 1.53. Okay, that's fine. You just keep it the way it is. Now, I take this sliding bar and drag it so that that thing moves and it goes all the way to the end. Okay, and then insert. Remember, we have done these things. Insert, rewind, and change this thing to anything but 1. And if you want to move it, continuously in one direction, it goes like this. But if you wanted to loop it in 2 different directions, excuse me, it goes like so. There are no physics. This is just a cartoon. Okay. So we stop this thing and rewind it and say, okay, now we're going to put some physics into the problem. All right. So if I go and click on f of x, this thing opens up. And then when I click on the mechanism, only the stuff related to the mechanism pop up. There is time and there is a length. And this length is that distance 1.53. Right now it's 1.53. However, what I want to do is I want to move this thing down. So I'm going to say this distance, that distance is equal to, not 1.53, add a formula, equal to 1.53. Don't forget inches. Dimensions must add up properly, or entities must add up properly. So 1.53 inches plus the velocity was 10 inch per second, inch divided by 1s. Or if you want, you can write 10 times 1 inch over 1 second. That's entirely up to you. Look, I can write it like that, or I can write it as 10 times 1 inch divided by 1 second. You just have to make sure that whatever you do eventually adds up inch equal to inch, and there are no syntax errors. If I had left out probably probably that star, I don't know, it might have given me an error or something like that. We can try it. And then time. Time is right here. Double click on it, it puts it right there. And if there are syntax errors, we're going to get it up right here. It says they're not homogeneous. So, oh, I forgot this. Oh, there's cancel. No. There's, oops. Let's try it again. Let's double click on this. I had an extra I here. That's what it's saying. I don't understand what you did. So this is times 10 times, not 10 I times. So you just left it there. And no errors. Oops. Is this something? Let me see for a second. This is good. Active. It says no. Let me see for a second. This is oh, we can. That's all right. Let's go ahead and see what's going on. I don't like that no message there, but that's okay. Oh, this is the law. Okay, let me right click activate. Something must be wrong here. Let's try to make a change here, see whether it makes a difference, because I don't like the fact that it says not active. And let me, I don't think it has anything to, I'm pretty sure it has nothing to do with what we did. 10, okay, that's what I did. 10 inch, 10 inch divided by 1 second. Okay, 1.53 inches plus 10 inch divided by 1 second times time. Yeah, see this thing, I thought that updating this would come on. You know what? I don't like this, so let me delete it. Let's do another one. Okay, so one more time. On the mechanism, right there, this is the dimension, this is the length dimension, add a formula equal to 1.53 times 10, 1.53 times inches, IN, plus 10 times 10 inches divided by 1 second times time. I'm hoping that I won't get that on the time. Double click and say OK. Yeah, look, I don't know, that business of changing the units and then doing it again, it messed it up. It should have worked. It will work, but I did it again and just I don't have this deactivate sign there. Very good. Let's save it, by the way. All right, so we're going to do simulation with laws. So let's do simulation with law, and then later on we're going to put a sensor here and plot the velocity and stuff like that. So let's do simulation with laws. Now, default is 10 seconds. So 10 second time 10 inch per 10 inch per second, that's going to be 100. That's a lot of, so let's make it 1. That's a lot of distance that's going to travel, which it won't, obviously. So that's going to be maximum of 10 inches. So this is, even this is too much, but we'll find out. So if we play this, actually it reaches down below before 1 second. You know that, but I'll just leave it the way it is. That's okay. That's okay. That's fine. So we say close. Now we're going to create a sensor here, speed acceleration sensor right there. Speed acceleration, click on it. This is the ball rolling down the hall. And I want the reference product is that wall. And the point that I want to plot something is going to be this point. And it's going to be the y component later on, y component of the velocity. Okay, so that's good. And now we're going to go and click on the simulation with loss. Simulation with loss, activate sensor. Activate sensor. Now, if you don't get the whole thing, let me cancel that for a second. We did create it here, right? Yep, it's right there. So let's try it one more time. Where is that ball rolling down a hall? Down. Oh, we already have it. I don't want to do another one. So let's see. Let's double check on this. Yep. Activate sensor. Yep. Activate sensor. So what do we want? We want the only thing we want is the y linear speed. Y linear speed. Okay, y linear speed right there. See, notice change from yes to no. I'll move this thing out of the way. Let me move the tree up there. And then we're going to play. Remember, 1 second actually is too long a time, but that's okay. We're just going to go. All right, and we can make this graphics, and it's going to show you the velocity component of y of that point as a function of time. There we are. Okay. Now you might say, "Oh, why does it look like that?" Okay, so what we can do is let me close this. Okay, let me change number of steps. Rewind this thing. Make sure you clear the history. And let's change this thing to more steps, 80 steps, okay? Everything is the same. You just like clear the history and change this thing from 40 to 80. Play it. Notice that it actually looks like it did go further, but that's okay. Graphics. So you can cut down on this amount. This is actually the discontinuity. This is actually discontinuity in the the speed. Basically, suddenly jumps to a certain value. So anyway, just remember on the test, if I ask you to generate something like that on the final exam, first of all, zoom out here. I did zoom out, the usual zoom out, and then you're going to go print screen, start a, for example, a Word document, paint the stuff, paste the stuff in it, file, file, save as. We have the folder there called slider, no, not slider crank, slider crank. I don't see it here, so let me go ahead and it was called sliding ladder, right? So browse sliding ladder. That was from yesterday. Sliding ladder, desktop, sliding ladder. Must be somewhere down here. Sliding ladder. Yep. My plot of y velocity versus time. Remember, on the final exam, we will ask you to generate stuff, graphs like this. I don't want any more than I asked for or any less than I asked for. If I say, show me the y component of the velocity as a function of time, this is the only graph that must be on that paper. Okay? Nothing else.